Okay, yeah, I know. That's become a very common thing in American physics time. We're talking today about projectile motion. So if you could please write down the objective, as we said, was describe, model, and calculate projectile motion, which is like the one we had last time, except now instead of linear motion, it is projectile motion. What's a projectile, Alexa? Projectile motion. Lily, projectile motion.
Anything that travels through space. An object that moves through air or space. That's the exact definition in the book. That's what it says.
Yeah. When we think of projectile motion, you're not wrong. I wouldn't say an object traveling through air or space. Yeah, you're not wrong. Saying. I'm gonna let's define it a different way. Let's define it as opposed to linear motion. What was linear motion? In a movement in a straight line. So if we are contrasting that with projectile motion, we're going to call it, in fact, we might even call it non-linear motion. It doesn't have to be, and that's where your definition comes in, but this is the usual definition, non-linear motion, implying that it's in a, not just implying, but by definition, a curved path. We will talk later in the year about circular motion, which is motion in a curved path also, but we'll talk in that case about a more fundamental centripetal force, which is kind of like a category the forces can be in, as opposed to a specific projectile motion, which we usually think about as a moving object acted on by gravity. I like that a little bit better. It's probably still not perfect. I have no illusions that this is perfect. I'm saying this is a slightly broader definition. Broader than this, but not as broad as anything that moves, because you had said anything that moves, which is I don't love that one, especially because we need to differentiate between linear motion and projectile motion. The first thing that your book talks about is the idea of vectors and vector addition. We will go into some mathematical detail on these, but I want for you to watch the Mechanical Universe before we do that. To the extent that usually on the Chapter 3 test, there is some vector addition. If we don't get to that through the Mechanical Universe in time for the test, we'll probably just wait until we do it with forces, because we do it again with forces, and it might, but we'll see. Anyway, for now, whatever the case, for now, we're not going to talk about vector addition at this time, other than to mention that there is a difference between vector and scalar quantities. You remember that? Vector quantity, define, please. Yeah, a vector quantity is one that has magnitude and direction. Whereas a scalar quantity has only magnitude. We could, and there are physical science videos that I have. There are good ones too, but there are ones that I have that were taken when you guys were learning physical science about examples of vector and scalar quantities. So we're not going to really delve too deep into that. Just know that the vector quantities must have direction, like velocity and acceleration, which we talked about in the last video too. So even if you can't remember physical science, we also did just talk about it too. Projectile motion is that moving object acted on by gravity. And there are several different examples of this. The classic examples is of a thrown object. In fact, that's probably where this word projectile comes from. Something that has been projected in the somewhat archaic sense that it has been thrown. Is probably where the phrase projectile motion comes from. But if we throw this, is it moving horizontally? And I'm defining the x-axis in this direction in this diagram. Is it moving horizontally along the x-axis? This is the path that it took. I don't know if I made that clear. But if you throw something, does it move horizontally? This is not a trick question at this time. Yes, it does move horizontally. Does it move vertically? Yeah, it has both vertical and horizontal motion, and therefore it follows a curved path through space, and that's called projectile motion. Another classic example is this of, that your book mentions, of a ball falling off of a table. Does it have some horizontal motion? Yeah. Does it have some vertical motion? Sure. Yeah, it doesn't have to be thrown in that way. It just needs to have both a horizontal and vertical, I keep using this word, component of motion. In general, what does the word component mean? Yeah, part. Component. Yeah, it's like a part. Could we graph just the x component of this motion, meaning just the way it's moving horizontally? Could we graph that? Yeah, it's probably actually. If we did, let's say what's a good thing to be thrown? Lily's suspiciously human-shaped cat. Yeah, we'll draw that. We'll pretend this dot represents Lily's suspiciously human-shaped cat. That Alexa, this is Alexa now. That's how you change a stick figure into Alexa's. You just draw a hair. But Lily's suspiciously human-shaped cat, as it's being thrown, has this kind of horizontal motion. I'm trying to be very specific with my increments here because it should have, and I don't know if you can tell, but the increments should be what? Yeah, the same. As if it were rolling on a friction-free surface only under its own inertia. Just, you can throw it away, but it's up to you. Thank you. Thank you, Tiana. Okay. Please write that down. I said it, and I'm not going to write it because it's going to take too long, and I don't want to spend that much time on it. But do write that down. It's also in your book. The x component, the horizontal component of motion, is just as if that object had been rolled on a frictionless surface. It just carries on in a straight line in a constant speed forever. This line isn't straight, it's curved because there's another component to the motion. Speaking of the other component of motion, loudly, what is the other component? The y component here is like what? The up and down motion of this object is like what? Yeah, Alexa made some little noises, Lily made a little noise, but I want it to be in human English words. What is the y component of this motion going to be like? If the x component was like it rolling frictionlessly, up and down, okay, that's a good start, up and down. Just like that, though. Please be more specific. Let's do it in little dots again. Little dots again, let me show you. What are you supposed to be noticing about that? Like in what, though? What do we call this? This is in... We had a specific name for this state. Free fall. This is just like it's in free fall. It's just as if... So this... Give me the yellow ball. Alexa, give me the yellow ball right now. Okay, now throw it over here. This, I'm trying to make sure this is on camera. I can't do... I probably could if I had any... I was going to say I don't have any video editing skills. It's not really about the skills. If I had any desire to do video editing to spend that much time on this, I would slow this down right now, but maybe you can still kind of watch it. I'm going to throw this to you, okay? I'm going to throw this in projectile motion to you. Throw it back, please. The x component of that, the horizontal component of that, is just like if I rolled this, if there was a table, a perfectly friction-free table between me and Lily, and I rolled it along at a constant speed. It would be going at a constant speed. And the y component is just like if I throw it up in the air and then let it fall down again. Does the x component change? Does the motion in the x component change? No, it doesn't. It's moving in a straight line at a constant speed, which we know, straight line. Please don't get confused. The object itself is not moving in a straight line. I'm saying that the x component is as if it were moving in a straight line at a constant speed, 0 acceleration. And this is like it's in free fall. Meaning, what's remarkable about free fall? You remember? Is it accelerating, first of all? Yeah, it is. You can tell because the motion is changing. As it goes up, getting slower, which is a type of acceleration. And then as it goes down, it's speeding up, which is a type of acceleration. So this does have an acceleration. Downward acceleration, which, assuming this is on Earth, is what? 9.81 meters per second squared. It's just a combination of those two things. Those are the two, x and y, those are the two components that together add up to projectile motion. It is not anywhere near this simple to actually add these things together. The real math comes in. There's a lovely picture of this on page 34. You could have just paused that. I didn't have to hold it up there that long. Go back and pause it after I say this. The red one is being dropped. It's just being dropped straight down. And you can see, so what the picture is showing here is that those white lines represent a certain distance. I don't know what the distance is, but they represent a certain distance. The balls represent balls. And every certain time frame, a new picture is taken. And then they're overlaid on top of each other so that the distances between the balls represent the same time. The one being dropped is in free fall. What are the different, if we're assuming the time between shots is the same here, what does the larger distance towards the bottom mean that is happening? Speeding up. It's accelerating downward. And do you see that that exact same thing is happening downward with the yellow ball? Even though the yellow ball also has an x component, doesn't it? Now, I wish they had done this, but look at the grid. Imagine a vertical grid through the yellow balls. What do you notice about them? What's true of if there were imaginary vertical white lines through each of the centers of the yellow balls, what do you notice about that? Same distance, meaning if they're the same time, that there was no acceleration. No acceleration. And that is projectile motion. That is projectile motion. So let's draw that on here. Let me use blue for my ball again. We got that boy, that boy, that boy. Sorry, I'm not doing a super hot job of making them how I want to make them, sorry. That boy, that boy. Help. Okay, I'm doing every other one on the x component because I have more x component ones than I do y component ones. So I didn't really plan this out super good to how I wanted it to be. But we should notice, if this drawing is even remotely good, I'm going to use red for this bit. We should notice, please stop mocking me. We should notice that these are even. They're the exact same. Ideally, these get closer together. The vertical component of motion. And I'm going to do this one with green. We should notice that these, the horizontal component of motion, I only did every other one, and I kind of messed up big time on some of them, and the drawing was not super to scale to begin with. But we should notice, and you can kind of tell from that, after doing every other one, we should notice that they're equidistant. Same distance covered for the same amount of time. So it's a similar thing. And you notice that in real life too. It's a lot easier to see in larger and like bigger arc of projectile motion, bigger. By the way, what conic section is this? Do you know? What? Parabola. Yeah, it's a parabola. Very good job. So really, it should probably look more like that. But whatever. Anyway, if we have a larger parabola and a larger object and probably a slower moving object, you do notice this a lot easier. But you do notice. You do notice it getting faster. And a lot of people, the misconception here, and this is, if you didn't notice, the way that your physics tests suss out if you have a misconception is they give you a trick question. And one of the answers is what lay people think the answer is. Do you know what I mean by lay people? In science, we say lay people when we mean morons. Yeah. So it's what people think of this, and people think that it's just getting faster. The whole thing is just getting faster as it goes down, right? We know, because we're scientists, that the y component is accelerating, but that it has the same horizontal velocity throughout. And that's a very common misconception. Certainly it can cover more ground. Like if you're thinking about someone on the football field throwing, you want a faster throw because it'll cover more ground, but that won't necessarily indicate a higher altitude, and similarly, throwing it higher does not necessarily mean farther, other than that it stays in the air longer. So make sure you don't fall into the trap of misconception. There are ways to calculate this, and in fact, we don't need any more math to calculate this other than the equations we used last time, which are v equals gt and d equals 1/2 gt squared. Those are still the two equations that we're using. There is this idea of vector component addition, which is important for you to do, and you are welcome to do it the way the book says, which is the parallelogram method. But effectively it's this. Your book shows it as a parallelogram method, but I prefer a trigonometric method because you should be able to do trigonometry. It's not that difficult to do trigonometry. If we have two components of motion, or two components of any physical fundamental force, or not just force, but any physical attribute, we can just add those together by breaking them down into their x and y components, adding their x and y components, and then calculating the hypotenuse of that triangle. These ones, we would just multiply by the square root of 2 to find or we could use Pythagorean theorem, multiply, if this is 1 and this is 1, as you can tell, they're very similar. Come on, give me a break. If this is a regular right triangle or a isosceles right triangle, then we could just multiply this one by the square root of 2. And then based on this, we could also use the Pythagorean theorem. A, B, golly, thanks Lily, and C. We can use the Pythagorean theorem, a squared plus b squared equals c squared, to find any of those sides also. The point is that we set those up against each other and use them to find the resultant. That's what we call the hypotenuse here, the resultant. There's also, I should have started with this, but more simpler, more easy to understand ways to start with this. If I have an airplane, and this is the example your book uses, if I have an airplane, this looks like an angel. If I have an angel, and if the angel is flying at 10 meters per second, and there's a tailwind also of 5 meters per second, exactly what we would say in sailboat terms, right aft. If it is exactly the same direction, coming right aft, right from the exact same direction as the angel, we just add those together, algebraically, arithmetically, 15 meters per second is the resultant. That's easy. Same thing if I have now a headwind. Now what is it? Yeah, subtract it. Now it's 5 meters per second is my resultant. That's the simplest way. Then when they have angles, we do this, if they're right angles. But I kind of want you to forget about this because there's a way that I want you to do this that I think is better, and that, like I say, is the trigonometric way. We're not going to worry about that so much right now, but when we get to doing addition of forces, we will go into more depth in the trigonometric method of resolving vectors is what we call it. Do you have questions about projectile motion in general, or the very little bit about vectors that I showed you so far? Her says no. Her other one says no.